This presentation is delivered by the Stanford Center for Professional Development.
Today I'm going to keep talking a little bit more about another procedural recursion example, and then go on to talk about kind of the approach for recursive backtracking, which is taking those procedural recursion examples and kind of twisting them around and doing new things with them. Okay. This is the last problem I did at the end of Wednesday's lecture. It's a very, very important problem, so I don't actually want to move away from it until I feel that I'm getting some signs from you guys that we're getting some understanding of this, because it turns out it forms the basis of a lot of other solutions, end up just becoming permutations, you know, at the core of it. So it's a pretty useful pattern to have understanding. This is list the permutations of a string. So you've got the string, you know, A, B, C, D, and it's going to print all the A, C, D, A, B, C, D, A variations that you can get by rearranging all the letters. It is deceptively short piece of code that does what's being done here. Is that it breaks it down in terms of there being the permutation it's assembled so far, and then the remaining characters that haven't yet been looked at. And so at each recursive call, it's going to shuffle one character from the remainder onto the thing that's been chosen so far. So choose the next character in the permutation, and eventually when rest is empty, then all of the characters have been moved over and have been laid down in the permutation. Then what I have is a full permutation of the length n. In the case where rest is not empty, I've still got some choices to make. The number of choices is exactly equal to the number of characters I have left in rest. And for each of the remaining characters at this point, maybe there's just C and D left, then I'm going to try each of them as the next character in the permutation, and then permute what remains after having made that choice. And so this is just string operations here of attaching that rest sub I into the existing so far, and then subtracting it out of the rest to set up the arguments for that recursive call. A little bit at the end, we talked about this idea of a wrapper function, where the interface to list permutations from a client point of view probably just wants to be, here's a string to permute. The fact that keep this housekeeping of what I've built so far is really an internal management issue and isn't one I want to expose as part of the interface. So we in turn have just a really simple one-line translation that the outer call just sets up and makes the call to the real recursive function, setting up the right state for the housekeeping in this case, which is the permutation we've assembled at this point. So I'd like to ask you a few questions about this. To see if we're kind of saying the same things. Can someone tell me what is the first permutation that's printed by this? If I put in the string A, B, C, D. Anyone want to help me? Here's no.
A, B, C, D.
A, B, C, D. So the exact string I gave it, right, is the one that it picks, right? The very first time, and that's because if you look at the way the for loop is structured, the idea is that it's going to make a choice and it's going to move through the recursion. Well, the choice it always makes is to take the next character of rest and attach it to the permutation as its first time through the for loop. So the first time through the very first for loop, it's got A, B, C, D to choose. It chooses A. And now it recurs on A in the permutation and B, C, D to go. Well, the next call does exactly the same thing. Chooses the first of what remains, which is B, attaches to the permutation and keeps going. So the kind of deep arm of the recursion, making that first choice and working its way down to the base case, right? Remember, the recursion always goes deep. It goes down to the end of and bottoms out on the recursion before it comes back and revisits any previous decision. We'll go A, B, C, D, and then eventually come back and start trying other things. But that very first one, right, is all just the sequence there. The next one that's after it, right, is A, B, D, C, which involved unmaking those last couple decisions. If I look at the tree I have here, that may help to sort of identify it. That permute of empty and ABC, the first choice it makes is go with A, and then the first choice it makes here is go with B, and so on, so that the first thing that we get see printed out here will be A, B, C, D. We get to the base case. Once it's tried this, it'll come back to this one, and on this one it'll say, well, try the other characters. Well, there's no other characters, so in fact this one also finishes. It'll get back to here as it unwinds the stack, the way the stack gets back to where it was previously in these recursive calls, and now it says, okay, and now try the ones that have on the second iteration of that for loop, D in the front. And so it ends up putting A, B, D together, leaving C, and then getting A, B, D, C. And then so on kind of over here, the other variations. It will print all of the ones that have A in the front. There are 8 of them. I believe 6 of them that have A in the front. It will do all of those, and only after having done all of worked out that whole part, which involves kind of the exploration of this whole arm, will it eventually unwind back to the initial permute call, and then say, okay, now try again, go with B in the front, and work your way down, permuting the ACD behind it. So we'll see all the A's, then a bunch that lead with B, then the bunch that leads with C, and then finally the bunch that leads with D. It doesn't turn out matter actually what order it visits them in, because in fact all we cared about was seeing all of them. But part of what I'm trying to get with you is the sense of being able to look at that recursive code and use your mind to kind of trace its activity and think about the progress that is made through those recursive calls. So let me look at that code just for a second more and see if there's anything else that I want to highlight for you. I think that's about most of what I'm doing. So if you don't understand this code or there's something about it that kind of confuses you, now would be an excellent time for you to ask a question that I could help kind of get your understanding made more clear. So when you look at this code, do you feel like you believe it works, you understand it?
I don't have so much problem with this code, but I have a question. Is there a simple change you can make to this code so that it does combinations instead of permutations?
Does combinations, you meaning like just, we'll skip letters?
Right.
Yes, it turns out we're going to make that change in not 5 minutes. So in effect, what you would do, I mean, and there's a pretty simple change with this form, but I'm going to show you a slightly different way of doing it. But one way of doing it would be to say, well, given the letter, don't attach it to next, right? So right now the choices are pick one of the letters that remain and then attach it to the permutation. Another option you could do was pick a letter and just discard it, right? And so in which case I wouldn't add it into so far. I would still subtract it from here, and I'd make another recursive call saying, now, how about the permutations that don't involve A at all? And I would just drop it from the thing and I would recurse on just the BCD part. So a pretty simple change right here. I'm going to show you there's a slightly different way to formulate the same thing in a little bit. But anybody want to own up to having something that confuses them?
Actually, I was going to ask how what you would set up to test it.
So it's probably the easiest thing to do here, and I have the code kind of actually sitting over here just in case, right? Hoping you would ask. Is right now I just have the most bare bones sort of testing. It's like, yeah, well, what if I just throw some strings at it and see what happens, right? And so the easiest strings to throw at it would be things like, well, what happens if I give it the empty string, right? So take some really simple cases to start, because you want to say, well, what happens when you give it an empty input? Is it going to blow up? And it's like the empty input, right, immediately realizes there's no choices, and it says, well, look, there's nothing to print other than that empty string. What if I give it a single character string? Right, I get that string back. I'm like, okay, gives me a little bit of inspiration that it made one recursive call, right, and then hit the base case on the subsequent one. Now I start doing bigger ones, A and B. I'm seeing A, B, B, A. Okay, so I feel like, I got this. So if I put a C in the front and I put the BA behind, then hopefully what I believe is that it's going to try, C in the front, and then it's going to permute A and B behind it, and then similarly on down. So some simple cases that I can see. Verifying that it does produce kind of the input string as itself, and then it does the back-end rearrangement, leaving this in the front, and then it makes the next choice for what can go in the front, and then the back-end rearrangement, and kind of seeing the pattern that matches my belief about how the code works, right, helps me to feel good. What happens if I put in something that has double letters in it? So I put APPLE in there, and all the way back at the beginning, right, I can a lot more of them, right? It grows quite quickly, right, as we add more and more letters, right? Seeing the apple, and stuff like that. There's a point where it starts picking the P to go in the front, and the code as written, right, doesn't actually make an accommodation for this P and this P really being different. So it goes through a whole sequence of pull the second character to the front and then permute the remaining 4. And then it says, and now pull the third character to the front and permute the remaining 4, which turns out to be exactly the same thing. So there should be this whole sequence in the middle, right, of the same P's repeated twice, because we haven't gone out of our way to do anything about that, right? So, but it is reassuring to know that it somehow didn't get confused by the idea of there being 2 double letters. For example, if I do this, if I just say ABA, right, something a little bit smaller to look at, right? A in the front, those permuted, B in the front, and then it ends up permuting these 2 ways that ends up being exactly the same, and then I get a duplicate of those in the front. So right now it doesn't know that there's anything to worry about in terms of duplicates. What's a really easy way to get rid of the duplicates? Don't think recursively, think use a set. Right? I could just stuff them in a set, right? And then if it comes across the same one again, it's like, yeah, whatever. So it would still do the extra work of finding those down, but would actually, like, I could print the set at the end, having coalesced any of the duplicates. To actually change it in the code, it's actually not that hard either. The idea here is that for all of the characters that remain, right, in some sense what I want to choose from is, of the remaining characters, unique, right, pick one to move to the front. So if there's 3 more P's that remain in rest, I don't need to try each of those P's individually in the front, right? They'll produce the same result. Pulling one and leaving the other 2 behind is completely irrelevant. So an easy way to actually stop it from even generating them is, when looking at the character here, is to make sure that it is that it doesn't duplicate anything else in the rest. And so probably the easiest way to do that is to either pick the first of the P's or the last of the P's, right, to recur on, and ignore the other ones. So for example, if right here I did a find on the rest of after I, do you see any more of these? And if you do, then skip it and just let those go, or, you know, do the first, don't do the remaining ones. So you could either look to the left or look to the right and see if you see any more, and if so, skip the, you know, earlier or later ones, depending on what your strategy is. Any questions about permute here?
The use of the wrapper function.
So the wrapper function, if you just look down here, right, it just looks like that, right? This is a very common thing. You'll see this again and again, and it tends to be that the outer call, right, it tends to have just sort of this, you know, solve this problem, and then it turns out during the recursive calls you need to maintain some state about where you are in the problem, you know, like how many letters you've moved, or what permutation you've built so far, or where you are in the maze, or whatever it is you're trying to solve. And so typically that wrapper call is just going to be setting up the initial call in a way that has the initial form of that state present, that the client to the function didn't need to know about. It's just our own housekeeping that we're setting up. Seems almost kind of silly, right, to have a function that has just one line that just turns it in, but basically it's just exchanging, setting up the other parameters. Okay. I am going to show you the other kind of master pattern, and then we're going to go on to kind of use them to solve other problems. This is the one that was already alluded to, this idea of a combinations. Instead of actually producing all the 4-character strings that involve rearrangements of A, B, C, D, what if I were interested in kind of the subgroups, or the way I could choose certain characters out of that initial input, and potentially exclude some, potentially include some. So if I have A, B, C, then the subsets or the subgroups of that would be the single characters A, B, and C, the empty string A, B, and C itself, the full one, and then the combinations of 2 A, B, A, C, and B, C. In this case, we're going to say that order doesn't matter. We're not, whereas permutations was all about order. I'm going to structure this one where I don't care if it's A, B, or B, A. I'm going to consider it the same subset. So I'm just interested in inclusion. Is A in or out? Is B in or out? Is C in or out? And so the recursive strategy we're going to take is exactly what I have just kind of alluded to in my English description there, is that I've got an input, A, B, C. Each of those elements has either the option of being in the subset or not. And I need to make that decision for every one, every single element. And then I need to kind of explore all the possible combinations of that, right? When A is in, what if B is out? When A is in, what if B is in? So the recursion that I'm going to use here is that at each step of the way, I'm going to separate one element from the input. And probably the easiest way to do that is just to kind of take the frontmost element off the input and sort of separate it into this character by itself and then the remainder, similarly the way I did with permute. And then given that element I have earmarked here, I can try putting it in the current subset or not. I need to try both, so I'm going to make 2 recursive calls here. One recursive call where I've added it in, one recursive call where I haven't added it in. In both cases, right, I will have removed it from the rest. So what's being chosen from to complete that subset always is a little bit smaller, a little bit easier. So this is very, very much like the problem I described as the choose problem. Trying to choose 4 people from a dorm to go to Flicks was picking Bob and then dividing everybody into Bob and not Bob, and then saying, well, Bob could go, in which case I need to pick 3 people to go with him, or Bob could not go, and I need to pick 4 people to go without Bob. This is very much that same pattern, 2 recursive calls. Identify one, in or out. The base case becomes when there's nothing left to check out. So I start with the input ABC, ABCD, let's say. I look at that first element. I just need to pick one. Might as well pick the front one. It's the easy one to get to. I add it to the subset, remove it from the input, and make a recursive call. When that recursion completely terminates, I get back to this call, and I do the same thing again, remaining input is BCD again, but now the subset that I've been building doesn't include A. So inclusion, exclusion are the two things that I'm trying. So the subset problem, right, very similar in structure to the way that I set up permutations, right, as I'm going to keep track of two strings as I'm working my way down. The remainder in the rest, right, things that I haven't yet explored. The so far is what characters I've chosen to place into the subset that I'm building. If I get to the end where there's nothing left in the rest, so there's no more choices to make, then what I have in the subset is what I have in the subset, and I go ahead and print it. In the case where there's still something to look at, I make these two calls. One where I've appended it in, one where I haven't, and in both cases, right, where I have subtracted it off of the rest by using the subster operation to truncate that front character off. So the way that Permute was making calls, right, was in a loop, and so sometimes it's a little bit misleading. You look at it and you think there's only one recursive call, but in fact it's inside a loop, and so it's making potentially n recursive calls where n is the length of the input. It gets a little bit shorter each time through, but there's always, however many characters are in rest is how many recursive calls it makes. The subsets code actually makes exactly 2 recursive calls at any given stage, in or out, and then recurs on that n-1 remaining. It also needs a wrapper for the same exact reason that permutations did. It's just that we are trying to list the subsets of a particular string. The fact that there's some housekeeping that's going along with it, which is tracking the subset so far, is something we don't necessarily want to put into the public interface in a way that somebody would have to know what to pass to that and to get the right thing. Anybody have a question about this guy? So given the way this code is written, what is the first subset that's printed if I give it the input A, B, C, D? A, B, C, D, just like it was with Permute, right? Everything went in. What is the second one printed after that? ABC, right? So let me look at my little diagram with you to help kind of trace this process, the recursive call, right? Is that the leftmost arm is the inclusion arm, the right arm is the exclusion arm. At every level of the tree, right, we're looking at the next character of the rest and deciding whether to go in or out. The first call it makes is always in. So at the beginning it says, I'm choosing about A. Is A in? Sure. And then it gets to the next level of recursion. It says, okay, look at the first thing of rest, that's B. Is B in? Sure. Goes down the red arm, right? Is C in? Sure. Is D in? Sure. It gets to here, and now we have nothing left. So we have S of A, B, C, D. With the rest being empty, we go ahead and print it and say, okay, well, there's no more choices to make. We've looked at every letter and decided whether it was in or out. It will come back to here and it'll say, okay, I've finished all the things I can make with D in. How about we try it with D out? And so then D out gives us just the ABC. After it's done everything you can do with ABC in, it comes back to here and it says, okay, well, now do this arm. And this will drop C off and then try D in, D out. And so it will go from the biggest sets to the smaller sets, not quite monotonically though. The very last set printed will be the empty set, and that will be the one where it was excluded all the way down, which after it kind of tried all these combinations of in, out, in, out, in, out, it eventually got to the out, 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 out case, which will give me the empty set on that arm. Again, if I reverse the calls, right, I'd still see all the same subsets in the end, they just come out in a different order. But it is worthwhile to model the recursion in your own head, to have this idea of understanding about how that it goes deep, right? That it always makes that recursive call and has to work its way all the way to the base case and terminate that recursion before it will unfold and revisit the second call that was made, and then fully explore where it goes before it completes that whole sequence. Anybody want to ask me a question about these guys? These are just really, really important pieces of code. And so I'm trying to make sure that I don't move past something that still feels a little bit mystical or confusing to you, because everything I want to do for the rest of today builds on this. So now if there's something about either of these pieces of code that would help you to, yeah.
What would be the simplest way to include that?
So probably the simplest way, like if you said, oh, I just really want to be in alphabetical order, would be to put them in a set, right? And then have the set do the ordering for you. But
so you said order doesn't matter? So,
oh, if you did care about how they got ordered.
Like, let's say you didn't want BCD to equal CDD.
So in that case, right, you would be more likely to kind of add a permutation step into it, right? So if BCD was not the same thing as ABC, right, it would be like, well, I'm going to choose. So in this case, right, it always the subsets will always be printed as kind of as a subsequence. So if let's say if the input was the alphabet, maybe this is the easy way to describe it, all of the subsets I'm choosing will always be in alphabetical order because I'm always choosing A in or not, B in or not. If I really wanted BZ to be distinct from ZB, then really what I want to be doing at each step is picking the next character to go, and not always assuming the next one had to be the next one in sequence. So I would do more like a permute kind of loop. It's like pick the next one that goes, remove it from what remains and recur, and then I need that separate step we talked about of, and in addition to kind of picking, we also have to leave open the option that we didn't pick anything and we just kind of left the subset as is, right? So we could extend or not. And so permute always assumes we have to have picked everything. The subset code would also allow for some of them just being entirely skipped. So we'd pick the next one, right, and then eventually stop picking.
It's also possible just in your wrapper function then to maybe put a for loop or something like that, right, in which you're changing your string.
Yeah, you could certainly do that, like kind of permute from the outside too, right? So there's often very, multiple different ways you can get at the same thing, right? Whether you want to put it in the recursion or outside the recursion, have the set help you do it or not, that can get you to the same result. So let me try to identify what's the same about these, to try to kind of back away from it and kind of move to see how these are more similar than they are different, right? Even though the code ends up kind of having some details in it, that if you kind of look at it from far away, these are both problems that are about choice. That the recursive calls that we see have kind of a branching structure and a depth factor that actually relates to the problem if you think about it in terms of decisions. That in making a permutation, your decision is what character goes next, right? In the subset, it's like, well, whether this character goes in or not. That the recursive tree that I was drawing there that shows all those calls, that the depth of it represents the number of choices you make. Each recursive call makes a choice, right? A yes, no, or a next letter to go, and then recurs from there. So I make, one of those calls, and then there's n-1 beneath it that represent the further decisions I make that build on it. And so in the case of permutation, once I've picked the, n-1 things to go, there's only one thing left, right? And so in some sense, the tree is n because I have to pick n things that go in the permutation, and then I'm done. In the subsets, it's also n, and that's because for each of the characters, I'm deciding whether it's in or out. So I looked at A and decided in or out. I looked at B, decided in or out, and I did that all the way down. That was the length of the input. The branching represents how many recursive calls were made at each level of the recursion. In the case of subsets, it's always exactly 2. In, out, all the way down. So 3 starts at 1, branches to 2, goes to 4, goes to 8, 16, and so on. In the permute case, right, there are n calls at the beginning. I have n different letters to choose from, so it's a very wide spread there. And then at that next level, it's n-1, still very wide, and n-2. And so the overall tree has kind of an n times n-1 times n-2 all the way down to the bottom, which is the factorial function, which grows very, very quickly. Even for small inputs, right, the number of permutations is enormous. The number of subsets is 2 to the n, in or out, right, all the way across. Also a very, resource-intensive problem to solve. Not nearly as bad as permutation, but both of them, even for small sizes of n, start to become pretty quickly intractable. This is not the fault of recursion, right? These problems are not hard to solve because we're solving them the wrong way. It's because there are n factorial permutations. There are 2 to the n different subsets, right? Anything that's going to print 2 to the n things or n factorial things is going to do n factorial work to do so. You can't avoid it. There's a big amount of work to be done in there. But what we're trying to look at here is this idea that those trees, right, represent decisions. There's some decisions that are made, a decision is made at each level of the recursion, which then is kind of a little bit closer to having no more decisions to make. You have so many decisions to make, which is the depth of the recursion. Once you've made all those decisions, you hit your base case, and you're done. The tree being very wide and very deep makes for expensive exploration. What we're going to look at is a way that we can take the same structure of the problem, one that fundamentally could be exhaustive meaning tried every possible combination, every possible rearrangement and option, and only explore some part of the tree. So only look around in some region, and as soon as we find something that's good enough, so in the case, for example, of a search problem, it might be that we're searching this space that could potentially cause us to look at every option, but we're also willing to say if we make some decisions that turn out good enough, that get us to our goal or whatever it is we're looking for, we won't have to keep working any farther. So I'm going to show you how we can take an exhaustive recursion problem and turn it into what's called a recursive backtracker. So there's a lot of text on this slide, but let me just tell you in English what we're trying to get at. That the idea behind permutations or subsets is that at every level there's all these choices, and we're going to try every single one of them. Now imagine we were going to make a little bit less big a guarantee about that. Let's design the function to return some sort of state that's like, I succeeded or I failed. Did I find what I was looking for? At each call, I'll still have the possibility of multiple calls, an in, out, or a choice from what's there. I'm going to go ahead and make the choice, make the recursive call, and then catch the result from that recursive call and see whether it succeeded. Was that a good choice? Did that choice get me to where I wanted to be? If it did, then I'm done. I won't try anything else. So I'll stop early, quit going around the for loop, quit making other recursive calls, and just immediately unwind the recursion and say I'm done. If it didn't, it came back with a failure, some sort of code that said it didn't get where I wanted to do, then I'll try a different choice. And again, I'll be optimistic. It's a very optimistic way of doing stuff. It says, make a choice, assume it's a good one, and go with it. Only when you learn it didn't work out do you revisit that decision and back up and try again. So let me show you the code. I think it's going to make more sense actually if I do it in terms of looking at what the code looks like. This is the pseudocode at which all recursive backtrackers at their heart come down to this pattern. So what I tried to be abstract about here is, well, what does it mean to solve a problem, and what's the configuration? That depends on the domain and the problem we're trying to solve, but the structure of them all looks the same in the sense that if there are choices to be made, so the idea is that we cast the problem as a decision problem. There are a bunch of choices to be made. Each recursive call will make one choice and then attempt to recursively solve it. So there's some available choices, in or out, or one of next, or where to place a tile on a board, or whether to take a left or a right turn or go straight in a maze. Any of these things could be the choices here. We make a choice, we feel good about it, we commit to it, and we say, well, if we can solve from here, so we kind of update our state to so we've made that turn, or chosen that letter, or whatever it is we're doing. If that recursive call returned true, then we return true. So we don't do any unwinding, we don't try all the other choices, we stop that for loop early. We say, that worked, that was good enough. If this solve came back with a negative result, that causes us to unmake that choice, and then we come back around here and we try another one. Again, we're optimistic. Okay, left didn't work, go straight. If straight doesn't work, okay, go right. If right didn't work and we don't have any more choices, then we return false. And this false is the one that then causes some earlier decision to get unmade, which allows us to revisit some earlier optimistic choice, undo it, and try again. The base case is hit when we run out of choices, where whatever configuration we're at is like, okay, we're at a dead end, or we're at the goal, or we've run out of letters to try, whatever it is, right, that tells us, okay, there's nothing more to decide. Is this where we wanted to be? Did it solve the problem? And I'm being kind of very deliberately vague about what does it mean to update the configuration, or what does it mean for it to be the goal state? Because for different problems, it definitely means different things, but the code for them all looks the same, kind of in its skeletal form. So let me take a piece of code and turn it into a recursive backtracker with you. So I've got recursive permute up here. So as it is, recursive permute tries every possible permutation, prints them all. What I'm interested in is this this sequence of letters an anagram, meaning could be rearranged into something that's an English word. Okay, so what I'm going to do is I'm going to go in and edit it. First thing I'm going to do is I'm going to change it to where it's going to return some information. That information is going to be, yes, it worked, no, it didn't. Okay, now I'm going to do this. I'm going to add a parameter to this, because in order to tell that it's a word, I have to have some place to look it up. I'm going to use the lexicon that actually we're using on this assignment. And so when I get to the bottom, and I have no more choices, I've got some permutation that I've assembled here in so far, and I'm going to check and see if it's in the dictionary. If the dictionary says that that's a word, then I'm going to say this was good, that permutation was good. You don't need to look at any more permutations. Otherwise, I'll return false, which will say, well, this thing isn't a word. Why don't you try again? I'm going to change the name of the function while I'm at it to be a little more descriptive and call it isAnagram. And then when I make the call here, add my third argument, I'm not just going to make the call and let it go away. I really want to know, did that work? So I'm going to say, well, if it's an anagram, then return true. So if given the choice I made, I've got these letters X, J, Q, P, A, B, C, right? It'll pick a letter and it'll say, well, if, put that letter in the front and then go for it. If you can make it a word out of having made that choice out of what remains, then you're done. You don't need to try anything else. Otherwise, we'll come back around and make some of the further calls in that loop to see if it worked out. At the bottom, I also need another failure case here. And that comes when the earlier choices, right? So I got, let's say somebody has given me xj, and then it says, given xj, can you permute a and b to make a word? Well, it turns out that you know this ahead of time. It doesn't have the same vision you do, but it says xj, a, b. There's just nothing you can do. But it'll try them all dutifully. Try a in the front and then b behind it, then try b in the front and a behind it. And after it says that, it says, you know what? Okay, that just ain't working, right? It must be some earlier decision that was really at fault. This return false is going to cause the sort of stacked up previous is anagram calls to say, oh yeah, that choice of X for the first letter was really questionable. So imagine I've had like EX, TI. I'm trying to spell the word exit is a possibility of it. That once I have that X in the front, it turns out nothing is going to work out, but it's going to go through and try XEIT, XETI, and so on. Well, after all of those things have been tried, it says, you know what, X in the front wasn't it, right? Let's try again with I in the front. Well, after it does that, it won't get anywhere there. Eventually, it'll try E in the front, and then it won't have to try anything else after that because that will eventually work out. So if I put this guy in like that, and I build myself a lexicon, and then let me change this to anagram word. I can't spell. I better pass my lexicon because I'm going to need that to do my word lookups. Make this guy into a bool. And down here, oops, S lex. Okay. So I think that looks like it's okay. Well, no, how about I finish this thing off here? And so if I type in, a word that I know is a word to begin with, like boat, and I happen to know the way permutations work, right, is it will try that right away and find that. What if I give it tobe, which is a rearrangement of that, it eventually did find them. What if I give it something like this, which there's just no way you can get that in there. So it seems to, at least right now, it's not telling us what the word is. I can actually go and change it. Maybe that'd be a nice thing to say. Why don't I have it print the word when it finds it? If lex.contains word so far, then print it. That way I can find out what word it thinks it made out of it. So if I type tobe, well, look at that, boda. Who would know? That dictionary is full of some really ridiculous words. That one came back with exit. Let's type some other words. Query, so it's finding some words, and then if I give it some word that I know is just nonsense, it won't print anything, and it will return the false. And so in this case, what it's doing is it's kind of doing a partial exploration, right, of the permutation tree based on this notion of being able to stop early on success. So in the case of this last one, where I give it 6 nonsense characters, it really did do the full permutation, in this case, the 6 factorial permutations, and discover that none of them worked. But in the case of exit or the boat, that early in the process, it may have kind of made a decision. Okay, so for example, in this case, it will try all the permutations with Q in the front, right? Which means, okay, we'll go with it, and then it'll do them in order to start with, but it'll start kind of rearranging and jumbling them up, and eventually, right, it will find something that did work with Q in the front, and it will never unmake that decision about Q. It will just sort of have made that decision early, committed to it, and worked out, and it ended up kind of, there's a whole space of the tree that never got explored of R in the front, of Y in the front, of E in the front, because it had a notion of what was a satisfactory outcome. So a base case that it finally got to that, in this case, met the standard for being a word was all it wanted to find. And so it just had to work through the base cases until it found one. And potentially that could be very few of them relative to the huge space. All right. I have this code actually on this slide. So there's permute, and there it is turning into is anagram. And so in blue, trying to highlight the things that changed in the process, right? That the structure of kind of how it's exploring and making the recursive calls is exactly the same. But what we're using now is some return information from the function to tell us how the progress went. And then having our base case return some sense of, did we get where we wanted to be? And then when we make the recursive call, if it did succeed, right, we immediately return true and unwind out of the recursion, doing no further exploration. And in the case where all of our choices gave us no success, right, when we return the false and said, well, that was unworkable, how we got to where we were. So this is a transformation that you want to feel like you could actually sort of apply again and again, taking something that was exhaustive and looked at a whole space, and then had changed it into a form where it's like, okay, well, I wanted to stop early when I get to something that's good enough. A lot of problems, right, that are recursive backtrackers just ended up being procedural code that got turned into this based on a goal that you wanted to get to being one of the possibilities of the exploration. Anybody have any questions about what we got there? Okay, I'm going to show you some more, just because there are a million problems in this space, and the more of them you see, I think the more the patterns will start to emerge. Each of these, right, we're going to think of as decision problems, right, that we have some number of decisions to make, and we're going to try to make a decision in each recursive call, knowing that that gives us fewer decisions that we have to make in the smaller form of the subproblem that we've built that way. And then the decisions that we have open to us, the options there, represent the different recursive calls we can make. Maybe it's a for loop, or maybe a list of the explicit alternatives that we have that will be open to us in any particular call. This is a CS kind of classic problem. It's one that, it doesn't seem like it has a lot of utility, but it's still interesting to think about, which is if you have an 8x8 chessboard, which is the standard chessboard size, and you had 8 queen pieces, could you place those 8 queens on the board in such a way that no queen is threatened by any other? The queen is most powerful player on the board, right? Can move any number of spaces horizontally, vertically, or diagonally on any straight line, basically. And so it does seem like, that there's a lot of contention on the board to get them all in there in such a way that they can't go after each other. And so if we think of this as a decision problem, each call is going to make one decision and recur on the rest. The decisions we have to make are, we need to place, 8 queens, let's say if the board is an 8x8 board. So at each call, we could place 1 queen, leaving us with n-1 to go. The choices for that queen might be that one way to kind of keep our problem, just manage the logistics of it, is to say, well, we know that there's going to be a queen in each column. Right? It certainly can't be that there's 2 in one column, so we could just do the problem column by column. We could say, well, the first thing we'll do is we'll place a queen in the leftmost column. The next call will make a queen, place a queen in the column to the right of that, and then so on. So we'll work our way across the board from left to right, and then the choices for that queen will be any of the. And some of those actually are, we may be able to easily eliminate as possibilities. So for example, once this queen is down here in the bottommost row and we move on to this next column, there's no reason to even try placing the queen right next to it, because we can see that that immediately threatens. So what we'll try to do is there a spot in this column that works given the previous decisions I've made? And if so, make that decision and move on. And only if we learn that that decision, right, that we just made optimistically isn't successful will we back up and try again. So let me do a little demo with you. It kind of shows this doing its job. Okay. So the idea is I'm going to do it as I said, kind of column by column. The idea is that I'm placing the queen in the leftmost column to begin, and the question mark here says this is a spot under consideration. I look at the configuration I'm in, and I say, is this a plausible place to put the queen? And there's no reason not to, so that I go ahead and let the queen sit there. Okay, so now I'm going to make my second recursive call. I say I've placed one queen. Now there's 3 more queens to go. Why don't we go ahead and place the queens that remain to the right of this? And so the next recursive call comes in and says, if you can place the queens, given the decision I've already made, then tell me yes, and then I'll know all is good. So it looks at the bottommost row, and it says, oh no, that won't work. All right, there's a queen right there. It looks at the next one, and then sees the diagonal attack. Okay, moves up to here and says, okay, that's good. That'll work. Right, looks at all of them and it's okay. So now it says, okay, well, I've made 2 decisions. There's just 2 to go. I'm feeling good about it. Go ahead and make the recursive call. The third call comes in, looks at that row, not good. 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 Now this one, there just weren't any options at all that were viable. We got here, and given the earlier decisions, and so the idea is that given our optimism, right, we sort of made the calls and just sort of moved on. And now we've gotten to a situation where we have tried all the possibilities in this third recursive call, and there was no way to make progress. It's going to hit the return false at the bottom of the backtracking that says, you know what, there was some earlier problem. There was no way I could have solved it given the 2 choices, or whatever. We don't even know what choices were made, but there were some previous choices made, and given the state that was passed to this call, there's no way to solve it from here. And so this is going to trigger the backtracking. So that backtracking is coming back to an earlier decision that you made and unmaking it. It's a return false coming out of that third call that then causes the second call to try again. And it goes up and it says, okay, well, where did I leave off? I tried the first couple ones. Okay, let's try moving it up a notch and see how that goes. Then again, optimistic, makes the call, goes for it. Can't do this one. That looks good. And now we're on our way to placing the last queen, feeling really comfortable and confident, but discovering quickly, right, that there was no possible. So it turns out this configuration with these 3 queens, not solvable. Something must be wrong. Back up to the most immediate decision. She noticed it doesn't unmake, earlier decisions until it really has been proven that that can't work. So at this point it says, okay, well, let's try finding something else in this column. No go. That says, okay, well, that one failed, so it must be that I made the wrong decision in the second column. Well, it turns out the second column, that was the last choice it had. So in fact, it really was my first decision that got us off to the wrong foot. And now, having tried everything that there was possible given the queen in the lower left and realizing none of them worked out, it comes back and says, okay, let's try again. And at this point, it actually will go fairly quickly. That making that initial first decision was the magic that got it solved. And there we have a complete solution of the queens. We put it on to 8 and let it go. That you can see it kind of checking the board, backing up, and you notice that it made that lower left decision kind of, and it's sticking to it. And so the idea is that it always backs up to the most recent decision point when it fails, and only after kind of that one has kind of tried all its options will it actually back up and consider any previous decision as being unworthy and revisiting it. So in this case, that first decision did work out, the queen being in the lower left. It turns out there were, you saw the second one had to kind of slowly get inched up. In the second row, right, wasn't going to work, but the third row, tried that for a while, tried the fourth row for a while, all the possibilities after that, but eventually it was that fifth row that then kind of gave it the breathing room to get those other queens out there. But it did not end up trying, for example, all the other positions for the queen in the first row. So it really looked at a much more constrained part of the entire search tree than an exhaustive recursion of the whole thing would have done. The code for that, whoops, looks something like this. And one of the things that I'll strongly encourage you to do when you're writing a recursive backtracking routine, something I learned from Stuart Regis, who long ago was my mentor, was the idea that trying to make this code look as simple as possible, that one of the things you want to do is try to move away the details of the problem. For example, like is safe. Given a current placement of queens and the row you're trying and the column you're at, trying to decide that there's not some existing conflict on the board with the queen already being threatened by an existing queen, just involves this kind of traipsing across the grid and looking at different things. But putting in its own helper function makes this code much easier to read, right? Similarly, placing the queen on the board, removing the queen from the board, there are things they need to do. Go upstate the state and draw some things on the graphical display. put all that code somewhere else so you don't have to look at it. And then this algorithm can be very easy to read. It's like for all of the rows. So given the column we're trying to place a queen in, we've got this grid of Boolean that shows where the queens are so far, that for all of the rows across the board, if, right, it's safe to place a queen in that row in this column, then place the queen and see if you can solve starting from the column to the right, given this new update of the board. If it worked out, great, nothing more we need to do. Otherwise, we need to take back that queen, unmake that decision, and try again. Try a higher row, right? Again, assume it's going to work out. If it does, great. If it doesn't, unmake it, try it again. If we've tried all the rows that were open to us, and we never got to this case where this returned true, then we return false, which causes some previous one. We're backing up to a column behind us. So if we were currently trying to put a queen in column 2 and we end up returning false, it's going to cause column 1 to unmake a decision and move the queen up a little bit higher. If all of the options for column 1 fail, it'll back up to column 0. The base case here at the end is if we ever get to where the column is past the number of columns of the board, then that means we've placed a queen all the way across the board, and we're in success land. So all this code kind of looks the same, kind of standing back from it, right? It's like for each choice, if you can make that choice, make it. If you solved it from here, great. Otherwise, unmake that choice. Here's my return false when I ran out of options. There's my base case that says if I've gotten to where there's no more decisions to make, I've placed all the queens, I've chosen all the letters, whatever. Am I where I wanted to be? So there's some sort of true or false analysis that comes out there about being in the right state. How do you feel about that? You guys look tired today. And I didn't even give you an assignment due today, so this can't be my fault, right? I got a couple more examples, and I'm probably actually just going to go ahead and try to spend some time on them on Monday because I really don't want to give you a little bit more practice with those. So we'll see. I'll do at least 1 or 2 more of them on Monday before we start talking about pointers and linked lists. And so I will see you then. But have a good weekend. Come and hang out in Termin with me.